Good afternoon. This is a demo video for Aero 210 and Aero 315. Today I'll be doing example problem 3.1 from the text, and this will help to facilitate your understanding of example 3.1, chapter 3, continuity and mass flow rate. So to begin, I like to start with green engineering paper. It's the most ideal way to do it, of course not required, but this is good engineering practice. And of course, you always want to put a good header. So we'll put our section. I'll just pick M4 for now. You want to put the date, right? Today's the 22nd of the year 2021. You always want to put the problem number, right? So that you and your instructor know example which problem you're working on, and of course your name, right? So this is good practice to get into for labeling problems. Okay, so if you remember back, we have a well-defined problem here in example 3.1. Flows through a tube in a cross-sectional area in a way similar to the tube illustrated in 3.3. And 3.3 is right here. You see the area of the tube narrowing as it goes from station 1 to station 2. At a point in the tube, station 1, where the cross-sectional area is 1 meter squared, the density is 1.2 kilograms meter cubed, and the flow velocity is 120 meters per second. At another point, station 2, the cross-sectional area is zero point 0.5, which is smaller than the original, and the air density has decreased to 1 kilogram per meter cubed. And it's asking us to find the mass flow rate through the tube and what is the velocity at station 2. This is what we call a well-defined problem. If you remember back to chapter 1, to solve a well-defined engineering problem, we're going to use the GFASECSS method right there. The example problems in general are good tools to use in the absence of an instructor, a good supplement to your reading. Of course, the answers are all presented there. So let's look at this. You might notice right away that there's a correction here that I've been made. And if you recall back, we have the textbook errata, which are the errors that we've found in the book and that we need to bring them to your attention. And sure enough, right there, page 78, example 3.1, the units of area are meters squared, not meters cubed. And so I make that correction here for your knowledge, as well as you should be making these corrections in your text. So let's get started. Okay, and using the problem solving method, I list my givens. I have an area at station 1 of 1 meter squared. I have a density at station 1 of 1.2 kilograms per meters cubed, right? Stuff in a volume. And I have a velocity at station 1 of 120 meters per second. It's also telling me that I have some information at the other station. Area at station 2 is 0.5 meters squared, and the density at station 2 is 1 kilogram per meter cubed, right? Density is mass in a volume, stuff in a box. That's how I remember it. Okay, what am I asked to find? Well, in the problem statement, you're asked to find the mass flow rate, m dot, and the velocity at station 2. What kind of assumptions can you make? Well, for this case, in all of our Aero 315 and Aero 210 problems, you can always assume a perfect gas to start. Okay, that's one of your first assumptions. What are some of the other assumptions? Well, if you reference page 115, the summary section of chapter 3, it has a nice summary of the assumptions. Now you'll notice I've made some corrections. To use the mass flow rate equation and the continuity equation, in our course, we make some assumptions to help simplify the problem down to a more algebraic form. First of all, we like to assume that the velocity is perpendicular both to the entry and exit area and throughout the flow field. We also assume that it's one-dimensional flow from the lecture and reading. We assume that flow is steady. And from page 77, not printed here, we say that there's no nuclear reactions. Mass is neither created nor destroyed in our flow field or in our stream tube. So let's go ahead and make those assumptions for this problem. So we say perpendicular flow. I'll just write this to abbreviate. 1D flow and steady flow. And finally, I'll say no nukes, no nuclear reactions. So those are your assumptions. Now, if you're looking carefully, you'll see that there's another assumption down here, incompressible flow, which we will discuss shortly. Actually, we'll discuss it right now. Can I make this assumption of incompressibility? Well, let's look at the problem. Well, by definition, density is not constant. Density is changing. So therefore, this is a compressible continuity problem or a compressible flow problem. Furthermore, if you recall back at the beginning of the course, we highlighted a page called Fundamental Aero Equations to Memorize. And right there in the about a quarter of the way down, it says memorize the airspeeds where compressible flow effects must be considered. Anything above 330, 100 meters per second, 225 miles per hour, or Mach 0.3, these are all equivalent. And there it is, 100 meters per second. And sure enough, right at the beginning, we already exceed that. So this case tells us that we are in the compressible continuity. If it was a lot less and density was constant, we would use the incompressible continuity equation. So what is the next step? Given, find, assume, sketch. This lends itself for an excellent sketch. And here's my stream tube or my tube that is changing in area. I have flowing air in and I have flowing air out. And there are properties, right? We have area at station 1. We have velocity at station 1. We have a density at station 1. We also have something similar here. We have an area at station 2, velocity at station 2, density at station 2. And by now you should realize there's also an m dot, a flow rate in and a flow rate out. And these are both what? At station 1 and at station 2. Okay, so that's it. Sketch. What's next? Given, find, assume, sketch. E, equations. What equation am I using? Well, I have m dot, which is rho AV, which is mass flow rate. I also have m dot 1 equals m dot 2. Mass going in has to be mass going out, mass flow rate. If you recall back to the lecture, mass is conserved, neither created nor destroyed. Therefore, what goes in has to come out. But what's changing? The area. This is also equivalent to rho 1 A1 V1 is equal to rho 2 A2 V2. Okay? These are the equations we'll leverage. Let's see. Given, find, assume, sketch equations. Convert. Is there anything to convert? Well, all my units are relatively, yep, they are all consistent. So I'm going to NA this step, NA. And then the next step is solve. What does it mean to solve? Well, in this case, the first thing it's asking us to find is flow rate. And since we know that flow rate is the same everywhere, we only need to solve it at one point. And we already have the given values at station 1. So m dot at station 1 and everywhere else is going to be rho AV. And we will go ahead and plug in our known values. So 1.2 kilograms per meter cubed times 1 meter squared times 120 meters per second. Now, what am I expecting here? What kind of units are flow rate? Well, it's mass flow rate. So it's mass, kilogram, in this case, over seconds. Kilogram over seconds, or mass per time. That's what I'm expecting out. So can I confirm that here, right? Well, I can make this, make that look like a fraction, and that's gone because it cancels. I've got 3 mass meters upstairs and 3 meters downstairs, so that's gone. And what am I left with? Well, I'm simply left with kilograms and seconds. So I can multiply this straight across without having to do any conversions. And when you do this, you'll find that it equals 144 kilograms per second, m dot. And this is the same everywhere, right? So the next thing it asks you to solve for is velocity. what is velocity at station 2? Well, how did we initially solve this? Well, we can leverage the continuity equation. M dot in equals M dot out. And we know those to be equal, right? Or at station 2. We can call this station 2. And this is station 1. So rho A V at station 1 must equal rho A V at station 2. And let's see, what do we have? We're given this, this, and we've already given those. We're given that, and we're given that. We only need to solve for that. So we have one equation and one unknown here to solve. So this is relatively easy, but I like to go through it for illustration purposes. Oops. That'll give you velocity at station 2. Okay. Now, you already have this value. This is m dot, right? You already have this value. So you could simply substitute that value in. And so now you have 144 kilograms per second over, let's see, the density here is 1.0 kilograms per volume meters cubed times the area, which we know is 0.05 meters squared. And what I'm expecting out, something in meters per second. So how can I prove that to myself? Well, let's see, I have 2 meters squared here, and that's going to cancel out, and I'm left with 1 meter at the bottom. And then I have a kilogram here, second, and kilogram here. And if you remember, given the fraction in the denominator, you'll flip this over and multiply. This will help cancel out our kilograms, and then meters will shift over to the top. And so that gives us the proper units. So we know that the units are correct. And when you run this, you will find, and I'm going to just cheat here a little bit, that it equals 288 meters per second. And we put a nice box around that. V2 is equal to that. Okay. What's the last step? Well, the last step is sanity, arguably the most important step. Let's think about how we can prove this as a reliable answer. It's not okay to just say matches the back of the book. That's not really. I want you to put some thought into this. So how can we prove that we think that this is right? Remember that what happened to area, right? And rho AV equals rho AV at station 1 versus station 2. Station 2, station 1. This is our sanity check. Well, we have to keep this equal sign honest. It has to be the same everywhere. But what changed? Area went down. Therefore, to keep this equation balanced, one of these two other terms must change. We were already given density. We expect that velocity will go up. Because this area has narrowed, it must speed up to keep the same mass flow rate. Just like putting your thumb over the garden hose in the video in the lesson prep. So this makes for an excellent sanity check, and you can write that up. I expect that as area goes down, velocity should go up, as this is also a compressible flow problem. So there you have it. That's example 3.1 as a demo and how I like to solve it. And at least for my students, this is what I expect that you will do and turn in for the assigned homework problems.